what we've got is a potential energy surface. It looks something like this with no maximum in it. And so we've got to locate the transition state. And the transition state is going to be the bottleneck, the place where the system least likes to be. And if we've got a particular energy, E, so we're coming in with a particular energy, E, then that position is going to be where the densities of states is a minimum. High densities of states are a good thing. That's where the system likes to be. And a low density of states is going to be anathema. And the minimum is going to be where the bottleneck is and where the transition state is going to be located. And as we come in, what happens is some of these vibrations change their character. Rotations and vibrations change their character. They go from being vibrations or rotations with quite closely spaced energy levels to ones with quite widely spaced energy levels. And so if we have the same amount of total energy, then there are clearly going to be a lower density of states for the widely spaced ones than for the narrowly spaced ones. And so what's happening is, as we come in along here, there are two things happening. One of them is the amount of energy is available is increasing, but the vibrations are getting more and more widely spaced. The levels are getting more and more widely spaced. The system is getting more and tighter and tighter, we can think of it as becoming. And so those two count against one another, and so what happens is the density of the states decreases and then starts to increase. And so this is the position of the minimum in the density of states, and that's where the transition state will be at this particular energy. And if we go up in energy, then it happens at a smaller internuclear separation. And these modes that change are called transitional modes. So we have transitional modes, and we also have conserved modes. So things like these CH stretches here going into CH stretches are conserved modes. Their frequencies are not changing very much. And we have to concentrate on the ones that are changing significantly. For example, these rotations going into vibrations, or translations going into rotations, or this umbrella motion going into a CH deformation mode. Okay, so this is work done on CH3 plus CH3. I hadn't put it with CH3 plus CH3 on the notes, so you might add that. Done by the Argonne National Labs. And what they show is that the calculation of the rate constant of K infinity depends very sensitively on the potential energy as the radicals approach. So the form of this potential energy here is absolutely key. I mean, that's what's determining how much energy is available, and the rate constant is very, very sensitive to that potential. So, and the calculated potential depends upon the level of theory used. And so here are several different calculations of this potential energy here for CH3 plus CH3, and you can see there are massive differences between them depending upon the level of theory that's used. And this is at higher resolution. Is that at higher resolution? No, that's at... Yeah, okay, that's at high resolution. That's way out here. And the calculated rate constant, the high pressure limit, they reckon from calculation could be more accurate than from experiment, provided you get that potential energy surface right. We'll see later on today that that's not absolutely correct, but they can get very, very accurate calculations, very, very accurate rate constants, provided they calculate the potential energy very well. And so these are calculations for CH3 plus CH3 with different potential energy functions. And so the black symbols here represent the experimental results, but we're going to refine those later on today. And then these are the different methods of calculation. And CAS-PT2, if you remember, is the better multi-reference calculation that we referred to earlier on. And that gives this curve here, which is very, very close to the experiments. And Harding et al. Argue that that's actually going to be more accurate than these experimental data for a variety of reasons. Well, you can see that not doing an accurate calculation of the potential energy function can give you very, very poor values for the potential energy and therefore for the rate constant, differing by a factor of 10, which is really quite surprising for a reaction of this sort. This is CH3 plus H, and so these are calculations again from the argon group. And these are the calculations, these are measurements made at high temperatures. I gave you a slide on these yesterday, shock tube measurements by Joe Michael. And then these are the measurements made by Mark Brouard that I told you about yesterday, and also some using a similar technique by Paul Seekins. And once again, the argon group would argue that this particular curve here is actually the most accurate representation of the rate constant. H plus alkyl radicals. Let's have a look at other alkyl radicals. We looked at H plus CH3. And what this shows is the potential energy surface for the reaction. So this is H coming into CH3. And you can see that if it comes, so red contours, so these are energy contours. Red contours are high energy. Blue contours are low energy. And so if the H comes in from this direction, it's not going to, it's going to be presented by a barrier, similarly in this direction. But if it's got a wide range of possible angles that it can come in at where it's an attractive potential energy surface. And you can see that as you make the molecule, so this is ethyl, and the red bits are more pronounced. And when we go through to this species, which is the tertiary butyl radical, then the red bits dominate. And as the hydrogen atom comes in, it's got to come in really very specific orientations. And that's reflected in the rate constant. So these are the rate constants for CH3 plus H as a function of temperature, H plus C2H5, C3H7, and then tertiary butyl there. And you can see that the rate constant is dropping by a considerable amount because of this exclusion region here. And there is something called the Gorin model that David Golden, who's at Stanford, has discussed extensively and used extensively, and that uses this idea of these excluded angles of approach. Okay, now let's go to something of a complication. We've looked so far at calculating for a very well-defined transition state, and then where we can use, we don't have to use variational theory, and then at radical-radical reactions where there's no obvious transition state, and we do have to use variational theory. There can be a complication which arises because of a potential surface that looks like this. And this is rather like what we had with OH plus DME, dimethyl ether. So what happens is the energy decreases and the system forms a van der Waals well. And so, if you like, that's OH coming in and interacting with the oxygen atom on DME or the hydrogens on DME and forming a strong attractive interaction. And then we go over the barrier and then into reaction. And there are two transition states. The inner transition state, which is the sort of normal rearranging the electrons transition state, and then the outer transition state somewhere over here, which is rather like those CH3 plus CH3 and CH3 plus H transition states, which would have to be determined variationally. And so what we're going to have are two expressions, if you like, for the rate constant, K inner, which is going to be defined by, at some particular energy, by the sum of states at the inner position divided by the densities of states, and then the same sort of expression for the outer transition state here, sum of states for the outer transition state divided by the density of states. And we can think of an overall time for reaction. How long does it take for us to get into this system and react? And that time is given by the sum of the reciprocals of the inner and the outer rate constants. So we can think of the reaction proceeding, and there's going to be a time, and we said that these transition states are bottlenecks, and so there's going to be a time to get through the outer bottleneck, and then a time to get through the inner bottleneck, and we go on through to reaction. And whichever of those bottlenecks is the slower, allows the slower passage, then that's going to be the one that dominates. And so the time scale for reaction is 1 over K inner over 1 over K outer, which then means it depends upon W inner and W outer. And the smaller of the sums of states, the energy E dominates the rate constant. This transition state acts as a reaction bottleneck. And here's potential energy surface for OH plus C2H4. And don't worry about all this stuff up here. We're worrying about this bit of the surface. There's van der Waals well, which has got an energy of minus nearly 8 kilojoules per mole, so relatively deep. And then this energy barrier here, and we go over to form this adduct, C2H4OH. And these are calculations on this system. First of all, here's the outer transition state, the rate constant if only the outer transition state existed. And that's fairly constant and pretty big. It's an attractive interaction. It's rather like a radical-radical reaction. And here's the inner rate constant. And that, as the temperature goes up, that goes up much faster and faster and faster and faster. And that's because we're here and we're going up in energy here, and those densities of states are beginning to increase much more dramatically than is the case for over here. And so as we go up in temperature, the inner transition state is going to be favored. And the net rate constant you would expect would be something like that, the reciprocal of the sum of the reciprocals, and it would look something like that. This is a fuller calculation of it using a macrocanonical model, and there's quite a big difference between those two sets of calculations. But just look at this Greenwald paper, and you can see very clearly the importance of these inner and outer transition states. And so these are fits to the experimental data using this model. Now, let's go back to OH plus dimethyl ether, and let's try and explain what would happen there. So if you remember, we looked at this surface before. So once again, there's a van der Waals well. There's a complication because there are apparently 3 transition states, but they are interlinked. So they act only really like one transition state. And so here is the rate constant that you calculate. This was what you'd calculate if you only worried about the inner transition state. And even if you include the outer transition state, it doesn't change very much what's going on over here. And these are fits to the experimental data. A lot of experimental data covering a wide range of temperatures, going from about 200 Kelvin up to 1500 Kelvin. And the theory reproduces it pretty well, and that's determined entirely by what's going on in this set of inner transition states. However, this is a set of measurements that were made at very low temperatures, temperatures of around about 40, 50 Kelvin. And the rate constant now has got big again. So we seem to have gone through a minimum. And this is because the outer transition state is now beginning to play its role. And there are two effects. One of them is that at these low temperatures, the molecular system hangs around in this van der Waals well for quite some time. And this allows it to tunnel through these barriers here. And so what's happened, and that's going to be, that process is going to become more and more effective as the temperature goes down, because the lower the temperature, the more they're going to want to hang around in this van der Waals well, rather than just dissociate back to the reactants. And so that's the explanation of why the rate constant begins to increase so dramatically at these very low temperatures. So the rate constant, although the rate constant is decreased substantially, by the time you get down to 40 Kelvin, it's something like what it was at 500 Kelvin. And this is a model, a master equation model, which takes account of these two transition states, the residence time in this van der Waals well and tunneling through this barrier. A reminder from yesterday, we talked about HO2 plus HO2. And if you remember, we said that at low temperatures, the rate constant is pressure dependent and involves the formation of H2O4. And then what happens is it behaves much more like an ordinary abstraction reaction, and the rate constant begins to increase. And these are two references from 1990 and 2002, and they differ from one another really quite considerably. These are measurements of the rate constant. And Michael Burke, in the reference I gave you yesterday, said it's difficult to discern which, if any, of the high temperature determinations is reliable. More measurements are needed under combustion conditions. But there has been a theoretical calculation of this system, and so this allows us to look at it more fully. And so they're high-level calculations, CAS-PT2, so this is what the surface looks like. And again, it involves two transition states. So HO2 plus HO2 can come in together and form H2O4. And the H2O4 can then dissociate. And at low temperatures, what happens is you can stabilize the system into this well here so that it's not falling back out again to form HO2 plus HO2, and then it can go on and react. And under these conditions, low temperature conditions, then this TS1 is the determining transition state. So they get good agreement with the low temperature data, but the calculated rate constants in red, notice that this is 0 atmosphere pressure, and then this is 1 atmosphere pressure, and they coalesce as you go up in temperature. And there's reasonably good agreement with the experiments at low temperatures, but the high temperature temperature dependence is quite significantly different from the experimental data. And so this gives us a little bit of insight into some of the things we've been discussing earlier on. So here's the H2O4 intermediate, and it's got quite a strong interaction. So these are 10 kilocalories per mole. And that's the arrangement. Those are oxygen atoms, those are the hydrogens, and those are the oxygen atoms. And you can see that hydrogen bonding is really the key to those interactions. And then there are two transition states two inner transition states going over to form the products. And these are those two transition states, TS2 and TS2 prime. So here's one hydrogen atom. there's another hydrogen atom there. And what we've done is we've broken this bond here, and so that hydrogen atom is sticking out there. And in this case, it's rotated. So this system around here is rotated relative to that one. So those are the two transition states. They're interlinked once again. So this is what I mean by these torsions and torsional motions or vibrational motions that are interlinked. And so this is the potential energy surface. And there's the transition state 2. There's the transition state 2 prime. And they are separated by a certain amount of energy, but you've got to take both of them into account. And this is what this calculation did in sorting out just what the rate of passage over this inner transition state, these inner transition states is. Okay, so that's HO2 plus HO2, and that resolves some aspects of that high temperature behavior, but doesn't explain why there is such a poor agreement between experiment and theory. Okay, now what we're going to do is we're going to talk about another technique, which is called the master equation, which allows us to treat pressure-dependent reactions and reactions that occur on fairly complicated surfaces with several intermediates on those surfaces. Okay, so a reminder of association reactions. So we've talked about this before. We applied the QSSA to this intermediate AB star that can either dissociate back to reactants or be stabilized collisionally. And we got this expression for the overall rate constant. And what we said yesterday, there are two problems with this model. The first is that it assumes that the rate constant for dissociation of AB star is constant independent of the energy of AB star. And that's clearly not going to be adequate because the more energy you put into a molecule, the more easily it will dissociate. And the other is that it assumes that stabilization occurs completely from AB star to AB. So you remove all the energy from AB star. But what happens is it actually happens in several steps. So these deficiencies are recognized in the Troy modification that we talked about. But really, it would be good to have a more fundamental and flexible approach. And that's what's provided by this master equation model. So this is a simple dissociation reaction, AB going to A plus B. So these aren't just necessarily atoms. These are more complicated than just atoms. So these are fragments. And what we've done is we've divided the energy into a series of what are called grains. And these might have a width of 50 wave numbers, say a kilojoule per mole or something like that. So we have a whole set of grains, and we can talk about the numbers of vibrations, numbers of states, rotational and vibrational states that have energy within that grain. It's obviously related to the densities of states, but we call it N of E, the numbers of states in those grains. And we can have energy transfer between the grains, collisional energy transfer between the grains, and we can have dissociation, and we could have association as well. And what we do is we set up a rate equation for the concentration of each grain. And we express this as a matrix equation. So C, sorry, I've changed the notation on the next slide, so I apologize for that. C is the concentration within the grain, and M is a matrix that describes all the various processes that are going on. And so those processes are dissociation association, and energy transfer up and down. Initially, we're just going to talk about dissociation. The time-dependent grain concentrations depend upon the initial concentrations and upon the eigenvalues and eigenvectors of this matrix M. And it turns out that the eigenvalue of smallest magnitude, they're all negative, these eigenvalues, but if we take the eigenvalue of smallest magnitude, then that turns out to be equal to minus the rate constant for the system.
And smallest absolute magnitude.
Small absolute magnitude, yeah. Okay, so here's the master equation. Just let's step through this. So rho is the concentration density. So it's not quite C that we had in the previous slide. It's the concentration density. If we add those densities up, they will sum to 1. Concentration density in a particular grain at energy E. K of E is the dissociation rate constant. We're just looking at dissociation now. And this tells us about energy transfer out of the grain at energy E. Sorry, this tells us about energy transfer out of the grain at energy E. And this tells us about transfer into that grain from all the other grains. And omega is the collision frequency. Okay. Downward energy transfer, what we do is we use what's called an exponential down model. So we assume that the probability of transferring from one grain at energy E to a grain at energy E prime depends exponentially on their difference in energy. And there's a parameter alpha in there. So what this is saying is that going a long way from a high energy to a low energy is going to have a low probability, but going quite a short way is going to have a much higher probability. That's downward energy transfer. Upward energy transfer is determined by detailed balance. So we can, what's going to happen if there were no reaction and we simply allowed the system to evolve, then it must go towards a Boltzmann distribution. And so the upward and downward probabilities must be related in such a way that you finish up with that Boltzmann distribution in the end. And so that's what we mean by detailed balance. So we can, having defined the downward energy transfer, we can get the upward energy transfer by detailed balance, and these are basically the Boltzmann terms. And then we can set up the matrix equation, and the solution is in terms of eigenvalues and eigenvectors. We call topic 1. And there's the solution, depending upon all the various eigenvalues and eigenvectors. But what we're interested in is the rate of change of A. So our molecule that's dissociating is A, and we want to describe the unimolecular dissociation for that. And it turns out that Ku, that dissociation rate constant, is equal to minus lambda 1, which is the smallest. All of the eigenvalues are negative. If we take their moduli, which is the smallest one of those moduli, that's lambda 1. And that corresponds to the rate constant. So the dissociation rate constant is the modulus of the smallest magnitude eigenvalue. In this calculation, we need microcanonical rate constants. So we have microcanonical rate constants there. And so we use electronic structure calculations, but transition state theory. The collision frequency omega is equal to a collision rate constant Kc times the concentration of the third body, where Kc is the rate constant for collisions and m is the concentration of the collider, which is the third body. And then the energy transfer model, we generally use an exponential down model for calculating upward transitions using detailed balance. Now, just let me, before we have our questions, just let me try to emphasize the difference between a rate a rate constant and a frequency, because people use them almost interchangeably. So a rate is equal to, say, minus dx by dt, which is minus k times m times x. So that's the rate of that process. It's got units of molecules per centimeter cubed per second. The rate constant is Kc. That's not the rate, that's the rate constant. And the frequency is a term that sometimes, so we're talking about the collision frequency in this case. That's the same as the pseudo first order rate constant. Pseudo first order rate constant, and that's equal to Kc times n. So that's equal to omega in the things that I've given you before. It makes me rather cross when you're refereeing a paper and people use these terms almost interchangeably, and they talk about rates when they're referring to rate constants. If from this series of lectures you could take this lesson, then that would be good. Okay, any questions? How are we doing?
Is there a physical basis for a master equation, or is it just a model?
There is a physical basis. Okay, yes, sorry. Is there a physical basis for the master equation? And I mean, it is a model, but basically what you are doing is you are describing the process of energy transfer between different states, some of which can dissociate. So it's a model of that, but it's an exact model of that, except insofar as you're using energy graining rather than the specific energy levels of the system. So it would be exact if what you did was to use all of the energy levels of the system, but that would be a massively complicated problem.
So are these grains sort of like quantization, or?
No, all you're doing is just dividing the energy space into little grains, and then looking at all of the energy states within those grains. Okay? And so down at low energies, there'll be relatively few energy states within those grains, but at high energies, it can be quite massive. Yep.
So in your dense images you're just talking about, for the downward energy transfer rate, like how do we model, how do we calculate the coefficient A and alpha, like the explain data?
Yeah, so the question there is, if you look at some of those terms in there, in that master equation, they're as yet undefined. If we So here we've got this alpha term here. We're making an assumption that energy is transferred in an exponential manner. The probability is exponentially distributed. So we're making that assumption, but we've got to parameterize it with that alpha, and I'll talk about that in just a minute. Okie dokie? Right. Okay, rate constants for collisions. We can think of a molecule as acting like a hard sphere. And so if we looked at the potential energy, V versus separation R, then what would happen is the molecules would come in and then they would hit this wall at some distance d. And that would be the diameter of the collision complex. So just come in and then bounce back again. A more accurate description takes account of the attractive interaction and the repulsive interaction between the molecules. And one expression that's widely used is the Leonard-Jones expression, which says that V of R is equal to 4 epsilon into sigma over R to the 12 minus sigma over R to the 6. So that's the attractive term going as R to the minus 6. That's the repulsive term going as R to the minus 12. That's sigma. And the depth of the well is epsilon. And you can determine these quantities, sigma and epsilon, using high-level theory, or you can get them from transport properties of molecules, from the viscosity or diffusion coefficients or whatever of molecules. Okay, so here's the hard sphere collision. So we're looking for the KCs that go into that collision frequency. This KC here and here. And this is the Leonard-Jones rate constant for collision. Takes the hard sphere one, then multiplies it by this quantity omega 22, and there's the expression for omega 22, where T star is KT over epsilon, where epsilon is that well depth. Okay, so that's the sort of expression that's widely used in mass equation calculations. So if you go, you can find out more about this from this paper by Jasper and Miller. And what they did was to do dynamical calculations looking at collisions between molecules using high-level ab initio potentials for interaction between them. And they also developed an approximate method. And from this, they determined the size of this alpha parameter that we talked about, which is also called delta E down, the average energy transferred in a downward direction. And there's, I mean, this is often used as a variable parameter, fitting parameter. But there is increasingly more and more understanding of the sorts of values that it can take up, and also its temperature or energy dependence. If you go to this paper here, Combustion and Flame, you can also find Leonard-Jones parameters which have been used to calculate omega. So these two papers together allow you to understand how to do this aspect of the calculation, calculating the probabilities of energy transfer and also the collision frequencies. Now, this is a book, a beautiful little book by a man called Hugh Pritchard, which discusses mass equation calculations. It's an old one, as you can see. Very, very few people did mass equation calculations in those days. But this is an important diagram here, which we need to understand. So log minus lambda for dissociation versus pressure at fixed temperature. So what we're doing is we're plotting, that should be lambda I, seconds to the minus 1, the modulus of lambda. And there are several eigenvalues. The total number of eigenvalues is going to correspond to the size of that matrix M. The size of it is an n by n matrix where n is the number of grains that we've got. So the number of grains, and there are going to be a lot of them, we're going to get an eigenvalue corresponding to that. We're going to get a number of eigenvalues which correspond to those total numbers of grains. only one of them, whoops, is the rate constant that we want, and that's this smallest one down here. And that shows the normal sort of behavior that we would expect, increasing with pressure and then reaching a limit, as we've discussed previously. So the numerically smallest eigenvalue gives the rate coefficient, and the figure shows the limits k infinity and k0. The other eigenvalues are what are called relaxation eigenvalues, internal energy relaxation eigenvalues. So we could imagine, if we start off with a molecule at 300 K, and let's assume that what we can do is suddenly heat it up to 1,000 K. What's going to happen is we're going to get collisional energy transfer, promoting the molecules up to higher energy levels, and they're going to dissociate. And that process will occur more quickly at high pressures and more slowly at low pressures. And the evolution of the system will be described by these eigenvalues here. Remember, I showed you an expression which gave the concentrations of the various grains in terms of the eigenvectors and the eigenvalues, summed over all the eigenvectors and eigenvalues. And those will apply at short times, relatively short times. What they do is they establish a steady state distribution, and the reaction then takes place from this steady state distribution. So let's see what we mean by that. So here's the dissociation taking place. And let's plot the number of molecules. Let's use this term rho, which is the concentration density, as a function of energy. And if we go to high pressures, then we'll get a distribution that looks something like that, which is a Boltzmann distribution. That's the high pressure distribution, whether or not we've got reaction. Now, supposing that's the dissociation limit there, these molecules over here can dissociate. And so what the collisions do is they establish this steady state distribution, which at the high pressure limit is the Boltzmann distribution. As we go down in pressure, then collisions occur less frequently, and there's an increasing competition between dissociation and activation and stabilization. And so this distribution here changes and might begin to look something like that. And so there are fewer molecules above the dissociation limit, and so the rate constant for dissociation is obviously smaller. But there is a steady state. So there's the steady state distribution, and it's been established during these short time energy relaxation processes that have pumped the molecules up into this energy range. Okay, so these then are all these internal energy relaxation eigenvalues. And if everything is working perfectly, then they are well separated from this smallest eigenvalue down here. Collisional relaxation occurs on a shorter time scale than reaction. So here's the time scale of reaction. Here's the time scale of energy relaxation. And during these time scales, a steady state distribution of the reactant is established, and this determines the rate constant. The steady state distribution depends on the pressure. At low pressures, you'll get more depletion at higher energies. At high pressures, you'll get the Boltzmann distribution. The steady state distribution depends on pressure and approaches the Boltzmann distribution at high pressure. That distribution is established at the high pressure limit. Okay, so we'll keep coming back to this idea of there being a reactive, an eigenvalue which corresponds to the rate constant for the reaction, and then these internal energy relaxation eigenvalues. There's some funny behavior going on up here, but we'll come back to that later on. Okay, I'll go fairly quickly through the next few slides. So this is what we have for an association reaction. So previously we had A going to B plus C. Now we've got B plus C going to A, and A coming back again to form B and C. And we've got rate constants Ka and Ku. And we'll assume that C is very much greater than B. That's important because these master equation models are first order, require first order processes. And so here's the equation that we had before that describes the dissociation problem. But now we've added this extra term here, which tells us about the rate of forming A from B and C. And that rate, I won't explain this in any detail, but basically it's the high pressure limit multiplied by the concentration of B and C, and this fraction phi, which is basically the rate constants multiplied by the Boltzmann distribution. And I won't rationalize that, it would take too long, but if you go to any book on molecular reactions, then you'll find a rationalization. And we now have two what are called chemically significant eigenvalues, because we've got two sets of species. We've got B plus C, we've got A, and A is coming back to form B and C. If we treated this system here, we would get, and the rate constants Ka and Ku are given by these expressions here in terms of lambda 2, the higher of the two eigenvalues. And lambda 1, the smallest eigenvalue, is actually 0, because that corresponds to the establishment of equilibrium. Supposing what we did was we removed this rate coming back again. So in other words, once we got to A, we stayed there. The molecule was formed and didn't dissociate back to form the reactants. Then we would have just one set of reactants and a single reactive eigenvalue. And in that case, that single eigenvalue would correspond to Ka. Okay? And here's how you need to sit down and think about this, but this is how the matrix that we had previously has been modified. So this square section here is exactly the same matrix that we had for dissociation. And then we've got rate constants for coming in to form A at a particular energy from the reactants. And then here we've got rate constants for dissociation of A to form B and to reform B and C. So that's the form of the matrix. Here are the grains of A, and then we've got B down there. And Ki, these rate constants, are only non-zero above the dissociation threshold. So a lot of these early on are going to be zeros. We can go to even more complex reactions. So this is A plus B coming in and forming an intermediate C, which can isomerize to form an intermediate D, which can then dissociate to form the products. And what we're doing is we're allowing this reaction to be reversible, that reaction to be reversible, but this reaction not to be reversible. So we've got one set of species, another species this well, and another species this well. So we've got 1, 2, 3 chemical species, and so we have 3 chemically significant eigenvalues. So these are the chemically significant eigenvalues there. And they're the smallest eigenvalues that we calculate from solution of the problem. We also have a set of energy relaxation eigenvalues, and it's important that those are numerically significantly bigger than these down here. So the number of CSEs is equal to the number of wells and sources. So this is a source, and these are 2 wells. In the present case, it's 3. If the final step to E plus F is reversible, then there are 4 CSEs. So we'll be coming back from out here. So there'll be 2 sources and 2 wells, 4 CSEs, but the system would be conservative, would establish equilibrium in the long term, and so the smallest eigenvalue would again be 0. Okay, let's say a little bit more about these chemically significant eigenvalues. The eigenvalues of M exhibit separation in magnitude. All are negative, and the majority are large in magnitude, and govern the time evolution of the energy transfer process, establishing these steady states. While a smaller group of eigenvalues, the CSEs, govern the chemical evolution of the system. At low temperatures, the number of CSEs corresponds to the number of distinct chemical species being modeled and is usually the sum of the number of wells and source terms in the model. The separation in timescales allows a matrix rate equation to be set up relating purely to the CSEs that's identical to the rate equation for the chemical system. We'll see that in a minute. The rate constants can be determined from an eigenpair analysis of the whole master equation. So the master equation gives you the rate constants you need for that coupled chemical system. It really is very neat the way it all comes out. This is only possible provided the IEREs and the CSEs are well separated in time. And we'll see some examples where that isn't the case. And there are some references there about CSEs, these chemically significant eigenvalues. Just let's think for a moment. I mean, I'll go through this very quickly, but this is an isomerization reaction, and we'll look at an isomerization reaction later on. So this is A going to B. And so what we can have is this block of the matrix tells us about the energy transfer processes within well A and the rate constants for loss of A to B. This tells us the same thing about B. And then these off-diagonal ones, this is telling us about the formation of B, the formation of B from A and the formation of A from B. And so here's the loss of A forming B. Here's the production of B from A in those processes that are in there. And so when you set up this matrix equation, you have blocks that look something like this. And for some of the reactions we'll look at, the systems are really quite complicated, and so you have lots of these blocks floating around. Let's see what we mean by those chemically significant eigenvalues from a purely chemical point of view. So let's have a look at that isomerization reaction, A going to B. So we've got 2 species and therefore 2 CSEs. The system is conservative, and so the smallest eigenvalue is going to be 0. What can we say about the other eigenvalue? Well, we can use exactly the same technique as we did on Monday. We essentially solved this, but in a slightly more complicated way, with a C at the end of here. But we can solve this really quite easily and quickly, setting up the rate equations, setting up the matrix in C, setting up the matrix MC, which is the rate constants for the transfers. And when you solve that equation, then you find that lambda 1 is equal to 0, and lambda 2 is equal to kf plus kr. And that's what's called the relaxation rate constant. So the eigenvalue that we get out of the master equation for the isomerization reaction is going to be that relaxation rate constant, kf plus kr. And we can, as we showed on Monday, we can separate those two, provided we know the equilibrium constant. And these eigenvalues are exactly the same as the CSEs that come out of the master equation. So the chemically significant eigenvalues map exactly onto the eigenvalues for this simple chemical system. little word about detailed balance. In an isomerization, the microcanonical forward and reverse rate constants obey detailed balance. So, in other words, going from the grain at energy E in A to the energy grain at energy E in B, the rate constants depend upon the numbers of states in those two grains, NAE and NBE. Similar arguments also apply to association and reverse dissociation steps. So, does detailed balance, so that's the microcanonical level, does detailed balance apply at the canonical level? And at the high pressure limit it certainly does, because we're operating from Boltzmann distributions. At lower pressures, it's not really been possible to demonstrate totally unequivocally that detailed balance does apply. It's been possible to show that it's very, very close to applying. There may be some slight error in it, but numerical calculations show that it's a very good approximation. An analytic solution has not been found which demonstrates unequivocally that it always applies. And you can find a discussion of this in this paper led by Jim Miller, and there are lots of references in it. So thermodynamics can be confidently applied to calculate reverse rate constants from forward rate constants, whatever the pressure, provided these IEREs and CSEs are well separated. I'm sorry about banging on about this, but you'll see just how important this is later on. If not, neither rate constant is really properly defined. Okay, right, it's break time, isn't it?